Hello everyone, our YouTube topic is a difference face recognition loss function on class imbalance classification problem. And this presentation is presented by Bo Yu, Zeyulo, Chang, and our project mentor is Brandon. So today our presentation or our video will go as follows. First, I will introduce the loss functions in mathematical perspective. We will see why those loss functions have more performance better on the face recognition field in mathematical way. And then Zhe Yu and Chang will talk more about the project details, what we have done in our project, and Chang will do the result analysis, including visualize the computation matrix and visualize the data embedding features on 3 dimensions, and so on. So before we start our presentation, let me ask you a very quick questions. Nowadays, in deep learning field, we have enough data and very high computation powers, such as we have many GPUs can use for training the model. So how can we design a very good model to have a very good performance? Basically, there are two ways. The first is to design a very good model structure, such that we have even the residue net to use the residue block to propagate the error without managing gradient problem, or the U-net, that's like a U-shaped net to upsampling the image to do the image semantic segmentation and so on. But there's another group of people focus their eyes on design very good loss functions. They try to develop these good loss functions to enhance the discriminate power so that it can achieve a better performance. So let's get this new loss function step by step. First, let's call back our commonly used cross entropy loss with the softmax functions. So in this figure, we can see this is a cross entropy loss, and W, and this is the softmax function, right? W here is last second layers, the weight between last second layers and the last layers, and X there is the last second layers output. So W transpose X plus B is the last layer's output, and we use the softmax functions to match the output to the probabilities. And then this is our softmax function, right? If we first fix B equal to 0, and then W transpose X can also be written as the normalized W times normalized X times cosine theta G. And this normalized is L2 normalization, and theta G is the angle between the weight W and the embedding feature X. So if we move the normalized W times normalized X to the left, we can rewrite the function as S times cosine theta equal to S times W divided by normalized W times X divided by normalized X. And this equation is pretty interesting. That is, if we normalize the last layer's weight and the last second layer's embedding features and multiply a scalar S, then the predictions will be only depend on the angle between the feature and the weight. So then we can plug these equations back to our cross entropy loss. We can say if we fix B equal to 0 and normalize W and normalize X, and our cross entropy loss will become ES times cosine theta yi divided by the equations. And these two equations are equal, right? And then we need one more step to get our first new loss functions called arc-phase loss, is that we can add a margin direct to the theta. And what does it mean to add a margin M to the theta? From the below figures, we can clearly see that if this is our original softmax functions, and each different colors represented by the H class, and we add a margin means we squeeze the feature vector of embedding features, or in another word, we enhance the intra-class feature compactness will also enhance the inter-class discrepancies, right? Or in another word, we can say we maximize the intra-class variance while also minimize the inter-class variations, right? And this is a flowchart from the original paper. You can see it normalizes the last second layers and normalize the last layer's weight and multiply together and compute the arc cosine to get the theta yi and add the margins, and then compute the cosine and cross entropy loss at arc phase loss. So the flowchart is pretty straightforward to introduce the arc phase loss computation steps. After we introduce the arc phase loss, now we come to the cosine phase loss. Basically, the idea is pretty same. So this is our arc phase loss we have been introduced, and this is the cosine phase loss. We can say the only difference is that it extracts m from the theta, but directly minus to the cosine theta. So why does the paper doing things like that? Because the author said doing this way can make the training process can enhance the training process because we don't need to compute the arc cosine theta yi anymore, and also it's more easily to let the gradient flow in the network. But the performance is also not as good as the arc phase loss. Then we come to the sphere phase loss. Basically, the idea is also pretty similar. So we can directly look the loss functions. We can say it doesn't normalize x, it keeps the normalized x, and it times the margins directly to the theta yi. So the paper doing this is because it makes a scalar changeable so that it can improve the performance. So now we can put these four loss functions together and to see basically sphere phase loss, cosine phase loss, arc phase loss, they both share the same idea, is that they enhance the intra-class compactness and also inter-class discrepancies, right? We can directly see from this figure. Now we come our fourth new loss functions called center loss. The idea is different from the previous three, and now we will introduce the center loss for you.
Okay, let me introduce the center loss function to you. Boyu has explained how to build an arc phase loss functions and cosine phase and sphere loss functions. Now, if we don't change the original softmax function and add a center loss function, LC, behind it, we can get a new joint loss function, L. And let me explain the LC. The XI denotes data point and CYI denotes the YI's class center of deep features. The center, CYI, should be updated at each mini-batch. Obviously, LC means the Euclidean distance between data point XI with the class center YI. The lambda is a hyperparameter. So why do we use the joint center loss functions? First, let's see the figure on the left. When we only use original softmax loss functions, the deep features of test data are not discriminative enough, since they still show significant intra-class variations, like here and here. Then, if we add LC behind the original softmax functions, we can get the figure on the right. The central loss penalizes the distance between the deep features and their corresponding class center in the Euclidean space to achieve intra-class compactness. The loss function can decrease the distance between data points in a same class. It can concentrate each class data points into each class center. In a word, center loss get data points together among the same class in feature space. The white dot, C1, C2 to C9, denote 10 class centers of deep features. When we choose a bigger lambda, deep features are more discriminative, like the figure shows. Properly choosing lambda such as 0.2 can improve the verification accuracy for our project. For this environment, our group use MNIST database. It's a database of handwritten digits from number 0 to number 9. There are almost 6,000 data points for each class. Also, our group have prepared 5 imbalance datasets. The number in the rectangle is the number of data points. The last 4 data sets are extremely imbalanced. Each imbalance class only contains 60 data points. Here, here, and here. Next, Chang will introduce the architecture of our net and present the results of our project.
For the architecture, we select the Net5 as our architecture. The Net5 is a simple convolutional network designed for handwritten and machine-printed character recognition. It consists of 2 sets of convolutional and average Pooling layers, followed by a flattening convolutional layer, then 2 fully connected layers. Convolutional layers use the 5x5 convolutions with thread 1. Subsampling layers are 2x2 average Pooling layers. Now let's focus on the second last layer, F6. So why the output is 84, not a power of 2? It is because the encoding of characters in the computer is ASCII2. These figures are represented by a 7 plus 12 bitmap. Selecting these sets can conveniently estimate the value of each pixel. Next are our results and visualization. The first one is softmax loss. We trained it with 100 epoch and the test accuracy is 92.9%. We extract the features of second last layer and reduce the dimension to 3 to visualize the results. We can see each class aggregate not so dense, and the edge of each class is very sparse. So its intra-class distance is large, and the inter-class distance is very small. This is the confusion matrix of softmax loss. For the majority class, we can see the samples of majority class are nearly are all classified right in each class. For the minority class, there are lots of misclassified samples, and they distribute average. Next is ArcVis loss. We trained it with 100 epoch and the accuracy is 93.45%. We can see there is an angle between each majority class, and for the minority class, they aggregate in the center. And they cannot be sharply separated. This is a confusion matrix of ArcVis loss. We can see for the number 7, there are a large amounts of number 7 misclassified as number 2. The next one is cosine loss. We also trained it for 100 epoch and the test accuracy is 93.23%. The performance of cosine loss is similar with ArcVis loss because they both use the angle parameter. The confusion matrix of cosine loss is also similar with Arquis loss. There are also large amount number 7 misclassified as number 2. The next one is center loss. We trained it with 400 epoch and the test accuracy is 91.39%. For the majority class, like the pink one, we can see it aggregates very dense, and for the minority class, like the orange one, it's very sparse. These are the results of all kinds of loss functions. For the softmax, Arquis, cosine, and sphere, we trained it with 100 epoch. Compared with softmax loss, the test accuracy of these three loss functions are higher than the softmax loss. For the center loss, because it is hard to converge, so we train it with 400 epoch, and the test accuracy is the lowest one. From the confusion matrix with softmax loss and Arquis loss, we can see the amount of number 7 misclassified as 2 sharply increase. To explore the reason, we focus on the sample of number 7. We find that there are lots of bad 7, like these pictures. So for the better performance, we will make the data set of number 7 and achieve better performance in confusion matrix. We can see the number of number 7 misclassified as 2 has decreased. Thanks for the instruction of Dr. Brandon, and thanks for listening.